This lesson begins to look at simple harmonic motion and the various energies associated with simple harmonic motion. Okay, so in particular, we're going to be looking at the energy of a spring, but the analysis extends into pendulums as well. The difference being springs having elastic potential energy and pendulums having gravitational potential energy. And then we're going to end with what I call endpoint analysis because there are special points in the motion of a spring or a pendulum that are important to look at. Okay, first off, in simple harmonic motion, what we have are two different energy sources that can constantly transform back and forth. Potential energy to kinetic energy and then back to potential energy and back and forth and back and forth. Okay, if we ignore friction, this process of transforming energy will continue forever. Okay, most of the systems, especially here on Earth, that we're going to look at, yes, we have friction, but to simplify our analysis, we're going to ignore that. Okay, so what's important to realize at this point is that the total mechanical energy is pretty much going to stay constant the whole time. Okay, the sum of my potential and the sum with kinetic, that's going to stay constant. Okay, so to calculate the potential energy of a spring, we have a formula for that where the potential energy of a spring is going to be equal to 1/2 k x squared. I usually say x squared, but in reality it's delta x. It's how far the spring has been stretched from equilibrium. Okay, if I was to do this for a pendulum, the potential energy of a pendulum is mg delta h, okay? How high the bob is from its lowest point or the equilibrium point. Remember, for a pendulum, equilibrium is straight up and down. For a spring, if it's horizontal, it's the midpoint, okay? And again, it's the midpoint vertically, okay? But it's also the equilibrium point where my weight and the gravitational force and the spring force balance out, okay? So in terms of endpoint analysis, what we're going to look at are three special points, okay? Those three special points being the positive amplitude, the negative amplitude, and the equilibrium point. The reason those three are special is because one of the energy sources, either potential or kinetic, is going to be zero at that point. And I have a table that helps you memorize it, but in general, I think it's better if you can derive those values. Okay, because what we're going to look at, the variables that are important for us to look at are potential energy, kinetic energy, velocity, force, acceleration, those types of things, okay? Amplitude as well. I mean, not amplitude, but position as well. Okay, so here's the table, okay? On the left side, we have five different variables, six because one's duplicated. The 5 variables mentioned plus position. Position, velocity, acceleration slash force, since they're in the same direction and correspond to each other, kinetic energy and potential energy. Across the top I have the 3 points, okay? Negative amplitude, the middle, and positive amplitude. Okay, and what we look at is whether a value is 0 at that point. Is my position or my displacement 0? Velocity is 0, or does it reach its maximum value? Maximum in magnitude, not necessarily minus. Okay, so it's basically absolute value. Okay, so to derive this table, you need to know the definition of position and amplitude, okay? Amplitude is the maximum displacement. So therefore, the position one will clearly reach a maximum at the amplitude points, a 0 at the other points. I only have zeros and maximums in this table. Velocity, on the other hand, at the endpoints, at those amplitude points, my object is changing directions from going one direction to the other direction. It must pass through 0 at those amplitude points. Okay, so just like when we were throwing objects in the air, at the top of the arc, the velocity of the object hit 0. The vertical velocity hit 0. Okay, so for the velocity line, we have 0 velocity at the endpoints and a maximum velocity at the equilibrium point. That's when it's hitting its greatest speed. Okay, acceleration and force. Remember, simple harmonic motion is proportional. The force is proportional to displacement. That's the definition. Okay, so my acceleration or force is going to be a maximum at the amplitude points, okay? F is proportional to delta x. So if my amplitude is at a maximum there, my acceleration or force will also be a maximum. Okay, kinetic energy, the formula for kinetic energy is 1/2 v squared, velocity squared. So it'll have the same line as the velocity line. And for the potential energy, for a spring, it's 1/2 kx squared. So it'll have the same line as your position. Okay, so that's the difference, okay? Or you can simply remember that since kinetic energy and potential energy must add up to the same number, my potential energy will be the opposite line to the kinetic energy. Okay, this table is easy enough to derive. I don't really want you to memorize it. However, I know a number of you love to memorize things because that's easier for you, and it's easy enough to memorize. Most of the time, a lot of students I find have memorized it incorrectly, and I believe it's easy enough to derive instead. Okay, so here's a problem for practice, okay? It deals with the string, and I want you to do some calculations, and we'll talk about this in class next time. Thank you.